Okay, so let's look at mixtures of gases, picking up where we left off. In general, when you're looking at a sample of gases, just by looking at your sample container, you cannot tell how many different types of gas are present in your gas sample. That's because in general, when we look at gases, regardless of how many different types of gases are present, they behave as one uniform pure substance, okay? That means that when we're doing ideal gas law calculations, we can calculate the total moles of gas molecules that are present just by knowing the pressure, the volume, and the temperature, regardless of whether the molecules of gas that are in the sample are different from one another. We can figure out the total moles of different gas molecules present just by knowing the pressure, the volume, and the temperature. Okay? But sometimes we want to get information about a specific gas. Okay? If we want to figure out what the pressure, for example, is of one single gas that's present in a gas mixture, that is called its partial pressure. So if the partial pressure of a gas is the pressure that only that particular gas is exerting within the total gas mixture. Okay, so we could look at the partial pressure of a gas in two different ways. Okay, if we know the fraction of the particular gas within the mixture, and if we know the total pressure of all of the gases, we can figure out the partial pressure of a gas sample. If we know the volume and the temperature of the gas sample, and if we know the number of moles of that particular gas that we're looking for that are present in the sample, we can also find the partial pressure of a gas in a gas mixture. And again, the partial pressure is the pressure that one particular gas out of all of the gases that are mixed together, the pressure that one particular gas is going to exert on its own within that greater gas sample. What it turns out is that the gases behave independently, okay? They're each going to exert their own individual pressures within the total mixture. And we can calculate the total pressure of a gas sample by adding up the individual partial pressures of all of the different gases that make a gas sample up. So if I have a gas sample and there are 4 gases in it, gas A, B, C, and D, and gas A has a partial pressure of 0.1 atm, B has a partial pressure of 0.1 atm, C has 0.1 atm, and D has 0.1 atm. My total pressure for the gases in that container would be 0.4 atm. Okay, so we would sum up the individual partial pressures of each of the gases, and that would give me the total pressure that's in the container. So when we solve for PV equals nRT for the ideal gas law, we're solving for the total pressure in that gas container. Okay, so we're not being specific about the type of gas molecule that's present when we solve for PV equals nRT. In this case now, we're going to start to look at the more specific gases. We're like, how can we find out information about the particular gases that are inside of a mixture? Okay, so to do this, we can, one method that I mentioned a couple of slides ago is that we can use the individual amount of moles of the gas to figure out the pressure of that gas. All right, so if I have a gas mixture and I have a few different gases in there, say I have 3 gases in a mixture, and gas 1 is 2 moles, gas 2 is 3 moles, and gas 3 is 4 moles. All right, to find the pressure of gas 1, I'm going to use 2 moles times RT divided by volume. Okay, and the temperature and the volume are going to be the same for all 3 gas samples. But when I calculate the pressure for 2 moles, that's only going to be the pressure for gas sample 1. Okay, so if I have 3 different samples and I calculate the pressure for gas 1 using 2 moles, the pressure for gas 2 using 3 moles, and the pressure for gas 4 using, wow, the gas pressure of gas 3 using 4 moles, and I get pressure values for each sample, then I can find the total pressure of my gas sample by summing up the 3 different partial pressures. Right? Another thing I can do is understanding that my total pressure is pressure A plus pressure B plus pressure C, and that relationship is equivalent to N, which is moles of A, times RT over V, plus moles of B times RT over V, plus moles of C, RT over V. I can actually pull all of those moles out of my addition, kind of using algebra. My common number here, or my common term here, is RT over V. So I could also take NA plus NB plus NC, pull it out of my equation, add those things together. I can add all of the mole values together, and I can multiply that value by RT over V to get my total pressure. Okay, and if I do that, then you'll see that we're back to our normal pressure ideal gas law formula, where our total pressure equals total moles times RT divided by V. Okay, another way that we can solve for partial pressure is by using the mole fraction of the gas that is present in the sample. All right, the mole fraction is the moles of the specific gas that you are looking for divided by the total number of moles that are present in the sample. And mole fraction is denoted by a capital X. So if you see X of A, that means that you're solving for the mole fraction of gas A, which means that you are taking the moles of gas A and dividing it by the total number of moles that are in a sample. The mole fraction does not have a unit, it's just a ratio. When we have the mole fraction, then we can take that mole fraction value and we can multiply it by the total pressure. The mole fraction times the total pressure will give us the partial pressure of the gas that we are looking for, the gas that is associated with the mole fraction value. So now we're going to look at this example. I'm going to bring it to the whiteboard so that we could do this out together. We have a 1 liter mixture of helium, neon, and argon. Total pressure of 662 millimeters of mercury at 298 Kelvin. The partial pressure of helium is 341 millimeters of mercury. The partial pressure of neon is 112 millimeters of mercury. So we want to know 2 things. What mass of argon is present in the mixture? What is the mole fraction of each gas? All right. Let me bring the problem back up so I can see it. Okay, so we're going to write out our different variables before we start. So our volume is 1 liter. Our total pressure is 662 millimeters of mercury. Our partial pressure of helium, so we're going to note that P of helium is 341 millimeters of mercury. And the partial pressure of neon is 112 millimeters of mercury. Okay, oh, and our temperature, let's put a comma. Temperature equals 298 Kelvin. Okay, so now we're going to think about how to approach this problem. I mean, the best way to start this is by asking yourself, what is the question looking for? Okay, and here the question is looking for the mass of the argon that's present in the mixture. Anytime that you're asked to find a mass value, we should be comfortable by now understanding that that is going to be directly related to a mole value, right? So we're going to need to know the moles of argon before we could figure out what the mass of argon is. And how are we going to calculate moles of argon? Well, it's a gas, so we're going to use our ideal gas law. Okay, so one of the variations of the ideal gas law that we just looked at was the fact that we can solve the ideal gas law for moles of argon specifically, as long as we know the partial pressure of argon specifically. Okay, so moles of argon is going to be the pressure of argon times the volume divided by R divided by T. Okay? Volume, R, and T don't change from sample to sample, but the pressure of each gas will be different and the mole value of each gas will be different. So we know the volume, we know the R, we know the T. Let's find the partial pressure of argon. I have my total pressure, which is 662 millimeters of mercury. Okay, so I'm going to subtract the pressure of helium. So we'll say this is the total. That's helium. And I'm going to subtract the pressure of neon. Oh, sorry about that. Got a little windy. And that is how I'm going to figure out what the pressure of argon will be. Okay, so 662 minus 341 minus 112. So my partial pressure for argon is going to be 209 millimeters of mercury. Now for the ideal gas law calculations, I'm going to need that in terms of atmospheres. So 209 millimeters of mercury, 760 millimeters of mercury in 1 atmosphere. That's 0.275 ATM. Okay, now that I have that calculation done, I'm going to use that information up here to figure out what my moles of argon are. So 0.275 ATM times 1.00 liters divided by 0.08206 times 298 Kelvin. Okay, I'm going to erase this other part. Okay, let's do some math. Okay, so that's my moles of argon. Once I have a mole value for argon, now I can find a mass value for argon. Right, so I can look at my periodic table. Argon is 39.95 grams per mole. Okay, so that's 0.449 grams of argon in that sample. Okay, now that's part A. Now part B says, yeah, well, what's the mole fraction of each of the gases in this sample? To find the mole fraction, I need to know the number of moles of each of the gases. All right, so to find the moles for each of the gases, I am going to need to do what I did here for argon for all of them. Right, so I want to take my pressure for helium and I want to convert that into atmosphere. And then I want to take my pressure for neon and convert that into atmosphere. Okay, so we'll do helium first. Okay, so this is my pressure in atmospheres for helium. This is my pressure in atmospheres for neon. And I'm going to box that off and keep it over here. I'm going to need those two values in a minute. But I'll erase this word. Okay, because now we want to do our ideal gas law calculation for both of these gases. So the moles of helium is going to be 0.449 ATM times 1 liter over 0.08206 times 298 Kelvin. And my pressure for neon, or my mole value for neon rather, will be 0.147 atmospheres, 1 liter, divided by our gas constant, divided by our temperature. Okay, let's get those values. So that's our mole value for helium. And this is our mole value for neon. And now we're going to use our mole values to calculate our mole fractions. Okay, so this is our mole value for argon from before. Now that's our helium, that's our neon. Those are the three numbers that we're going to need for the next part of this. Okay. Oh, so I'm going to erase this work here so that we can focus on the mole fraction part of it now. Now to calculate the mole fraction, first we're going to need to know the total mole values that we have. So our total moles will be 0.01125 plus 0.01836 plus 0.006011. That's 0.03562. So that's our total number of moles that are present. So now to find the mole fraction for argon, that is 0.01125 divided by 0.03562. The mole fraction for helium will be 0.01836 over 0.03562. And the mole fraction for neon will be 0.006011 divided by 0.03562. Okay, so you see how the units here all cancel out. So we're going to be left with just our simple ratios. Okay, so these are our three mole fraction values. That's the mole fraction of argon. This is the mole fraction of helium. This is the mole fraction of neon. And you'll notice that if you add these three values together, when you sum up the mole fractions of an entire gas sample, it should be very close to 1. So let's look at our next example. Okay, so turn to the next slide in your packet and let's look at this example. We have a sample of hydrogen gas mixed with water vapor. So that means that we have H2 gas and we have H2O gas. This is our mixture here. Right? Our mixture has a total pressure of 755 torr. Okay, so P total is 755 torr, and the water vapor has a partial pressure of 24 torr. What amount of moles of hydrogen gas is contained in 1.55 liters of this mixture at 298 Kelvin? Okay, so now we want to know specifically about the moles of hydrogen gas here. That means that we want the partial pressure of hydrogen for our ideal gas law equation. Okay, because we're going to set it up as moles of hydrogen gas equals the pressure of hydrogen gas times the volume divided by RT. Okay, so to find the moles of hydrogen gas, we have to find the pressure. We're going to take the total pressure, which is 755 torr, and we will remove the partial pressure of the water vapor from that. So minus 24 torr That gives us a partial pressure for the water vapor of 731 torr, which we want to immediately convert into atmospheres. And we remind ourselves that 760 torr is equal to 1 atmosphere. And we get a pressure of 0.962 atmosphere for our water vapor. Now that we have that value, now we can use our ideal gas law equation. So this will be 0.962 atm times our volume, which is 1.55 liters, divided by our gas constant, and our temperature of 298 Kelvin. And we get a mole value of hydrogen gas of 0.0610. Okay, let's look at our next example. We have a 12.5 liter scuba diving tank. Contains a heliox mixture made of 24.2 grams of helium and 4.32 grams of oxygen at 298 Kelvin. Calculate the mole fraction and the partial pressure of each component in the mixture and the total pressure of the mixture. So we have a few things to do here. We have a 12.5 liter tank, and it's at 298 Kelvin. We have 24.2 grams of helium, and we have 4.32 grams of oxygen. Okay, now, like we spoke about earlier, the big red flag for you when you're given amounts of gases in grams is that the ideal gas law requires mole values, not mass values. So we're going to right away want to calculate moles from these gram values rather. So we'll look at our periodic table, and we see that there's 4.00 grams of helium and 1 mole of helium. Which will give us 6.05 moles of helium. And an oxygen gas, which is diatomic, again, make sure that you remind yourself of that. There are 32 grams of oxygen and 1 mole of oxygen. So there's 0.135 moles of O2. Okay, so we could start by calculating the mole fraction. We can add these together to find the total number of moles that are present. That's 6.185 total. Okay, now we can find the mole fraction of each one. For helium, it'll be 6.05 divided by 6.185. And for O2, it's 0.135 divided by 6.185. Okay, so this is our mole fraction for helium. This is our mole fraction for oxygen. Okay, now we want to find the partial pressures and the total pressures of each one. Since we have the total moles of gas right here, and we have the volume, and we have the temperature, we might as well find the total pressure of the gas sample. So pressure total will be moles total times R over temperature and volume. Oops. Okay. So pressure total, moles total, RT over volume. And we have all of these values. So our total number of moles is 6.185. Our gas constant and our temperature is 298 Kelvin. We'll divide this by 12.5 liters. Okay, so you see all of this. We're getting rid of it. So our total pressure will be 6.185 times 0.0206. That will be our total pressure. Now to find the partial pressure, if we think back to that, to one of our versions of the Dalton's law of partial pressures, we could take the total pressure, multiply it by our mole fraction, that will give us the partial pressure. So let me draw a line here. So for the partial pressure of helium, I can take P total and multiply it by the mole fraction of helium. And I already have these two values, so that will be a very easy thing to do. 12.1 atmospheres times a mole fraction of 0.978. So my pressure for helium is going to be 11.8. My pressure for oxygen is going to be P total, which is 12.1 atmospheres, times 0.0281. 0.0218. And that will be, 0.264 atmospheres. Okay, so this is the partial pressure for oxygen. This is the partial pressure for helium. Okay, let's look at one more example here. A diver breathes a helium-oxygen mixture with an oxygen mole fraction of 0.050. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? So this question, when you approach it, might seem confusing at first because they're giving you information in a different way than normal. But start by writing down the things that you know. So our mole fraction for oxygen gas is 0.050. Okay, and it's a heliox mixture, so there must be a mole fraction for helium as well. Okay. We also know that the partial pressure of oxygen is 0.21 atmospheres. Okay, and we're looking for the total pressure. So let's think back to the definition or the formula for finding partial pressure, the one that we just used. If we have the partial pressure, of something like oxygen, or if we want to find the partial pressure for oxygen, we can take the total pressure and we can multiply that by the mole fraction. Okay. However, in this case, we don't know the partial pressure. We don't know the total pressure rather, but we do know the partial pressure and we do know the mole fraction. So we just know a different set of circumstances here. Okay. So if we want to find the total pressure, we can take the partial pressure of oxygen and divide it by the mole fraction of oxygen. So that's 0.21 atmospheres divided by 0.050. Okay, so this is the same formula we just used in the last problem, but this time we're solving for a different unknown value. And that gives us a total pressure of 4.2 atmospheres. Let's go back to our slides. So these are examples of how partial pressure affects us in real life, okay? Because it's important to know the pressure of certain gases in certain situations, because it can have a dramatic effect on, for example, the way that we breathe. We know that our own air is a mixture of gases, and the partial pressure of oxygen related to the other gases that are in the air that we breathe determines our own health, right, and our own ability to function normally. So there are different diseases that are related to various partial pressures of the gases in the air that we breathe. We have something called hypoxia, when our partial pressure of oxygen is low relative to the other gases that we're breathing. On the other hand, there's something called oxygen toxicity, which is a case where your partial pressure of oxygen is too high versus the other gases that are in the air around you. There's also nitrogen narcosis. That can happen more frequently when you're doing things like, for example, deep sea diving, and you would increase the nitrogen concentration in your body tissues by increased levels of nitrogen in the air that you're breathing. The next thing we really want to look at is how to collect gases experimentally. We don't actually get to see the gases that are being produced in chemical reactions. Sometimes we can see some bubbling or something like that. But when a gas is a product in the chemical reaction, it doesn't form in a tangible way, the way that like a solid precipitate does when we mix two aqueous solutions together and an insoluble product forms. So we need to find a way that we can collect and measure our gas products so that we can find out information about the gas products that are being formed. The way that we do this is that we collect gases over water. That's what it's called, collecting gases over water. And we set up these apparatus that are attached to water in either beakers or flasks or something like that. And as the gases in our experiment form, they kind of push the water out of the way. And because water is something that we can see and we can measure, as the gases push the water out of the way, we can keep track of them as they're being formed. So the volume of the water that is displaced during a chemical reaction is going to be equivalent to the volume of gas that is produced during that reaction. But because water evaporates, we also have to take into account the water vapor in the gas that we collect, okay? So our gas product kind of gets contaminated by the water as it's actually running through the water and pushing the water out of its way. So for us to find out information about our product gas in particular, we have to make sure that we remove the water vapor numerically from our reaction that we focus only on the gas that's being produced in a reaction. This is an example of the setup, a water displacement setup. So in this case over here in this test tube, we have metallic zinc solid mixing with hydrochloric acid. As the zinc oxidizes, it's going to see it producing H+, H2 gas, the hydrogen gas. And the hydrogen gas is released as bubbles. Okay, as it bubbles up, it's going to leave through a hole that's in this stopper up here. It's attached directly to this tube. So you see the gas traveling, the gas traveling. Well, the gas is looking for a way out, all right? So we want to know how much gas is being produced. So we put this beaker over here with water in it. We put it over the end of the tubing. So now as gas is being produced, gas is going to fill up the space here. Okay, and the more gas is produced, the more space it's going to need. So it's going to start to push the water out of the beaker into the surroundings here. And we're going to be able to measure how much water was actually removed from the beaker and pushed into the surroundings. Okay, but the gas that's up here is a mixture of hydrogen gas and water vapor because it picked up some water as it was pushing through. All right. Now, when we talk about the partial pressure of the water vapor, we're just going to call it the vapor pressure. All right. And that is only dependent on the temperature that our reaction is going to take place at. So there's a table in your textbook that relates temperatures and partial pressure of water or vapor pressure of water. This is not a table that you have to memorize, but whenever you are collecting gases over water, you have to use this table so that you can subtract the vapor pressure from the total pressure of gas that your sample is collected in. When we say the term a wet gas, that is a gas that has water vapor mixed in with it. And a dry gas is your isolated sample. So it's the gas once the water is removed. All right, so for example, if you collect hydrogen gas sample with a total pressure of 758.2 millimeters of mercury at 25 degrees Celsius, and you've collected this gas over water, what's the pressure of the hydrogen gas? All right, so to figure that out, we would look at the total pressure here, 758.2 millimeters of mercury. Then we would look in our table and we would see what the vapor pressure of water at 25 degrees Celsius was. Right? Once we do that, we're going to take our 758.2 millimeters of mercury, subtract the vapor pressure of water, and this remaining pressure value, 734.42, this is the vapor pressure of our dry hydrogen gas. Okay? Let's look at some examples of this. All right, so example 1, in order to determine the rate of photosynthesis, oxygen gas emitted by an aquatic plant is collected over water at a temperature of 293 Kelvin and a total pressure of 755.2 millimeters mercury. Over a specific time period, a total of 1.02 liters of gas is collected. What mass of oxygen gas in grams is formed? Okay, that's a lot of words right there. Let's focus in on the last sentence. What mass of oxygen gas in grams is formed? If we want to know what the mass of oxygen gas is, we're going to get that information by finding the moles of oxygen gas that are present. Okay, and to find the moles of oxygen gas that are present, that's going to require us to do our ideal gas law equation, but solving it for moles. So moles equals the pressure of oxygen gas times the volume over RT. Right? So this is what we're aiming to fill out. If we can find all the information so that we can fill out this part of our equation, we'll be able to solve for the moles of oxygen gas Once we know the moles of oxygen gas, then we can find the mass of oxygen gas. All right, so what other information are we given here? We have a temperature of 293 Kelvin. Now, it's nice that temperature is in Kelvin because we can plug it directly into our ideal gas law. But the temperature on our charts, on our vapor pressure chart, is in terms of Celsius. So we really quickly just want to know what this temperature value is in Celsius so that we can figure out the vapor pressure of water at this temperature. So we'll do 293. We'll take away our 273.15. And we get 19.85 degrees Celsius. Okay. Okay, now I'm going to look back a couple of pages into our vapor pressure chart. And I'm going to look for the vapor pressure of water. The closest one here is 19 degrees Celsius, or 20 degrees Celsius rather. So I think that we can take that. So we'll say that that's around 20 degrees Celsius for the purposes of our vapor pressure. So the pressure of water at 20 degrees Celsius is 17.55 millimeters mercury. Okay. Back to the problem. All right, we have a total pressure of 755.2 millimeters of mercury. Okay, and we collected 1.02 liters of gas. All right, so we want to find this information here. The thing that we are missing, right? We have temperature, we have volume, we know R. We want to find the pressure of oxygen gas all on its own. So the pressure for oxygen gas is going to be our total pressure, 755.2 millimeters of mercury, minus the pressure of the water vapor, 17.55 millimeters of mercury. The pressure for our oxygen gas is 737.65 millimeters of mercury. And now I'm going to convert that into atmospheres. And I get 0.9706 ATM. And that is the pressure of my oxygen gas, my partial pressure of my oxygen gas. Now I have all the information I need to solve for the moles of oxygen gas. So moles of oxygen will be 0.9706 times 1.02 liters. That should be ATM. Over 0.08206. Over 293 Kelvin. Okay, I'm going to erase this stuff over here. So the mole value for my oxygen will be 0.04118. The question asks, so for the mass of oxygen gas in grams, that's formed. So right away, I want to take that value, use my periodic table, and convert moles of oxygen gas into grams of oxygen gas. And remember, oxygen gas is diatomic, so it would be O2, not oxygen singular. And that is a value of 1.318 grams of oxygen gas. Okay, let's try that next example. A common way to make hydrogen gas in the laboratory is to place a metal such as zinc in hydrochloric acid. The hydrochloric acid reacts with the metal to produce hydrogen gas, which is then collected over water. We actually saw a visualization of that a couple of slides ago. Suppose a student carries out this reaction and collects a total of 154.4 milliliters of gas at a pressure of 742 millimeters mercury and a temperature of 25 degrees Celsius. What mass of hydrogen gas in milligrams does the student collect? Okay, so we're going to approach this very similarly to the last problem. First of all, we have a total pressure of 742 millimeters mercury. Okay, so I'm going to look back at the table. Pressure of H2O at 25 degrees Celsius. And I'm going to find the vapor pressure of water at 25 degrees Celsius. It's 23.78. Okay, that means that the pressure of oxygen gas is going to be 742 millimeters of mercury minus 23.78 millimeters of mercury. So let me get the pressure, oh, not the oxygen, hydrogen gas here. We're collecting hydrogen gas. Again, which is H2. It's diatomic. Review this if you do not remember what your diatomic gases are. Okay, so we have a pressure for our partial pressure for our hydrogen gas of 718.22 millimeters of mercury. And now I'm going to convert that into atmospheres because I will probably be needing my ideal gas law. So 760 millimeters of mercury, 1 atmosphere. And that is 0.945 atm. That's the partial pressure of my hydrogen gas. Okay, my temperature is 25 degrees Celsius, so that's going to be 298 Kelvin. And my volume, what was it? 154.4 milliliters. Which is going to equal 0.1544 liters. Okay, so I have all this information now. Now I can take PV equals nRT and I can solve it for moles and figure out my information about oxygen. So my moles of oxygen are going to be pressure for oxygen times the volume over R over T. Okay, so the moles of our oxygen gas are going to equal 5.97 times 10 to the negative 3 And we want to calculate this value in terms of, I keep on saying oxygen gas, it's hydrogen. We want to calculate this in terms of milligrams, not just grams. So 1 mole of H2 will be 2.016 grams of H2. Okay, and then 1 gram will have 1,000 milligrams. And that is 12.0 milligrams of hydrogen gas will be collected during the reaction. Okay. So that is pretty much where this portion of our lecture ends. Okay, so this is the first half of what you're going to be learning. This is the material that's going to be on your quiz on Wednesday, May 6th. So it's up to 6.6 in your textbook. That's what you're going to focus on. I'll have the second half of the chapter 6 lecture posted for you by the end of the weekend. Email me if you have any questions about this, and practice as many of these problems as possible.